Hey everyone, this is me Abinash, and today we will be solving a very interesting problem, which is to find out the largest BST subtree in a given binary tree. So basically, uh, a binary search tree is basically a binary tree where the root node is basically greater than whatever the maximum element present in the its left subtree, and it should also be less than the whatever the minimum element present in its right subtree. Okay, so this is basically the concept of BST. So basically, we are given a binary tree and we just need to return what is the size of that particular subtree, which is basically a BST, and that should be largest one. Correct? So there can be multiple BST present in the given binary tree. So we just need to return whatever the maximum or largest size of the BST, which is basically present in the binary tree. So for example, you can consider, okay, first of all, if you consider this particular tree, then you may encounter, okay, this particular subtree which is rooted at the node 5 is a BST, and this one is the largest one. So cool. So in that case, you will simply return 3. So 3 means how many nodes present in this particular subtree, including the root itself. Okay. So in that way, for example, if you will consider this particular tree, then you will find that, okay, the entire tree is a BST. So in that case, if we will consider any of the subtree, for example, the subtree rooted with the node 3 is will again be a BST, isn't it? Because for a tree to be considered as a BST, it should recursively satisfy the condition. Okay, the condition needs to condition which it should hold to be considered as a BST. Okay, it should be satisfied recursively for each and every node. Okay, so for that case, we can say that, okay, if the entire tree is a BST, then obviously each and every subtree rooted with itself, or that particular any particular node will again be a BST. Okay, so let's consider the subtree rooted with node 3. So again, this is a BST, isn't it? So if it is a BST, then can I say, okay, the largest size is only this? No, I should check for each and every node. Okay, that is okay. This is a PhD core. I'll save its answer and I will move further. Then I will find, okay, 5. If the subtree, the subtree associated with the node, or we can say the rooted with node 5, is this a BST? So yeah, it is a BST, and obviously it is the root of the original tree as well. So for that case, even we cannot have any higher value than this, because this is the original root of the tree, given tree. So for that case, we will simply going to return 7. Um, you know, this is the final answer. So what is actually happening? So let me tell you that, for example, if somebody wants to find out what could be the brute force approach to go and you know solve it. So for that case, one could easily think about one approach, that, okay, if what happens, let me pick my pen so that it can be easier. Okay, let's say you are right here. Okay, and you think, okay, so uh, let me find out if the subtree which is rooted with node 10 is a BST. So you find out, okay, this is not a BST. Cool. So you go to left and check for this node as well. Okay, this a BST? So if I want to, yeah, it is a BST, then you will say, oh, okay, is this okay? This is a BST. Then tell me what is its size. Then you'll again run a recursive call to find its size. Where the root node is this. Okay, rooted with node 5. Similarly, you will call for each and every node that, okay, is this a BST? Then if it is a BST, then find out its size. So in worst case, you will end up with n square solution. Okay, why? Because one recursive call will take care of the each BST part. I mean, it will check whether the subtree rooted with this given node is a BST or not, and if that is a BST, then it will just find out the size of the that particular subtree. So again, you can consider a tree which is skewed. Let's say this is a tree, and actually I'm this is a left skewed tree. Okay, you can just consider like that. Okay, just imagine. Okay, just imagine that this is a tree and this is a BST as well. The whole tree is a BST as well. So in that case, you will you are right here, let's say, and you find that okay, this but I'm sorry, you are right here. Okay, and you find that okay, this is a BST, right? So you will come here, you will see again this is a BST, you will come here again, this is a BST. I mean, uh, are you getting me? For example, you will find out okay, this is a BST, then you are again finding out the size of the BST, isn't it? Similarly, for each and every node, you are just calling the same function, and again, if this is a BST, then you are finding out the size. So this will work, no doubt. Maybe it won't work for larger case because this is n square solution. So what is the extra work that we are doing right here? We need to address that to solve the entire thing, okay, in most optimal way. So let's just think about the case. So basically we are moving below, in this manner we are just moving, and we are trying to see okay, each and every node that okay, if this is a BST or not. So if it is a BST, then we are finding out the size of that particular BST. Okay, so for that case, uh, we are end up with a complexity of n square. So why we should move each and every node to find out whether it is a BST or not? We actually do not need to take care of that. It can be taken care of by just parsing the information of the child to its parent. So for example, let's suppose okay, that this particular node is having the information of its child, both its left and right child. Let's say that if it is a BST, if it is a BST, then what is its size, and the min and the max element as well. So why min and max? Let me tell you. Okay, let me erase everything. Yeah, right. So now just let's take this particular example and let's understand the whole fact, the whole theory. Okay. Yeah. So for example, what I'm saying is we initially we were going all the way down, and for every node we were checking that if it is a BST or not. Now based on that fact, whether it is a BST, then we were calling the size of size function, for example, to find out the entire size of the BST. And we are in that way we were solving it. That is cool, but that was n square solution basically, as I have you know talking about. So we can reduce it significantly by parsing the information of the left child, or sorry, parsing the information of the child node to its parent. For example, 5, let's say 5 has the information of both its child. For example, let's say okay, this is a BST, right? 5, 1 and 8 it is complete full-fledged BST. So let's say 1 has returned that okay, I am a BST and my left and right child also BST, and the size of mine is, let's say, 1. So 5 has the information of 1. Similar case for 8 as well. Now 5 has two information. It has both true, let's say, let me write like this, true from true, which is saying that okay, the left child is a BST, the left subtree is BST, and the minimum, let's say, okay, there can be one more doubt, that why I'm finding the minimum and the maximum value from here, as I have already, said right here. So what is the significance of minimum and maximum value for any such node is, because I can see that one is in the left side, but my code doesn't know that where one is situated, where one is present initially. So if I just found out that, okay, the minimum and the maximum for each and every node, which is again the BST, then if I'm right here in 5 in some moment of time, then I can simply, check whether it is, greater than the minimum, the maximum of its left child and minimum of its right child. Okay, I hope you are getting. So the significance of minimum and maximum is only that the code doesn't know that where 1 and 8 are present. Okay, although I am, looking at it, I'm just figuring it out that, okay, one is present at the left side. So for me, I do not take care of that, min and max, because I know that where one is present at the left side of the 5. So to take care of this thing for my code, I just need to find out both min and max, correct? So the first thing I will be taking care of is, if this is a BST, okay, I'll be returning this piece of information to every parent, okay, from the child to every parent. Similarly, I'll be taking care of, if it is a BST, then what is its size, okay, correct. And note that I'll be returning 0 otherwise if it is not a BST, okay. Similarly, okay, I just found out that, okay, is this a BST? Then if it is a BST, then what is its size? And in third, I will be taking care of like mean, and at fourth element will be, taking care of max. And see, one more thing to observe here is, uh, whether or not a node is a BST, but I need to return its size. Okay, for example, right here one is a BST, that is why I need to return the size. I mean, I'm just finding out the size. Similarly, 5 is also, the subtree which is rooted at 5 is also a BST. That is why I'm just finding out its size as well. Now, if I would talk about 15, it is not a BST, okay, because 7 is lesser than it and it is in the right side. So again, I'm just trying to find out its size as well, okay. So for that case, size is, dynamic. It is changing, every time, wherever I am at. So for that case, I will be using a final answer. Let's call it final answer. So the final answer will be responsible for finding out the original size where the tree that I am currently looking at. I'm, for example, 518. It is a tree, isn't it? Okay, this is a PhD of the given tree, but every subtree is again a tree as well. Okay, so for that case, the final answer will be the size what I had found out initially. All right. So I hope you got it. I hope you got the root of this problem. Now let me quickly write down the code. You will, if you would not clear, previously, you will clear right here. Okay, you will be completely clear. Cool. So basically, let me define the structure that I will be following. Let me call it like container. Okay. Although container is a very long word, but it's okay. So the first element, the first information is, okay, is this a BST? Okay. Second one is, okay, if it is a BST, then what is its size? Then mean, then max. Okay. And finally, we are having a final answer, which is actual, thing that I will be using. Cool. So container is a long word. Let's simplify it. Let's call it node data. Okay. Cool. So right now I just have found out some things. So let me write down the base condition. Let's say there is no root, and that means I was initially given an empty tree, for example. So for that case, what will be the answer? What will be the size of the largest BST in that particular tree? Because there was no tree. So for that case, I'm simply going to return 0. Otherwise, I will, let's say, I have some function, let's say get size, okay, and I'll pass the a, and as my final answer is this, okay, containing actually the, the answer which I need in ultimate. So that is basically the final answer of this particular structure. So cool. Let me quickly fill it out. I mean, as I have written it, that means the function that I'll be creating will be of no data type. Cool. Get size. Okay. So right now we just need, I'm sorry, right now we just need to take care of few things. Okay. For example, uh, there there is no root. Let's say root is empty. I'm just, very left. I mean the leftmost element. For example, 1. I'm just the left of 1 as well. So right here it has nothing. I mean it is completely null node. So for that case, I just need to think that, okay, if I'm given a tree which is basically null, so is that a BST? See, if a single element is also a BST, okay, right? A single element is also a BST, as the property says. So a null node is also a BST. You just need to take care of few things, right? So if this is a BST, what I need to return is, okay, I will say that, okay, this is true. I mean, actually I'm filling out the, values of this structure. Okay, so this is a BST and the size of it is 0 because it is null. And the minimum, what is minimum, what is maximum? Let me tell you. The minimum is basically the maximum element, uh, you know of its left child, and maximum will be the minimum element from its right child. For example, this particular tree, right? So what is the, okay, what is the maximum element from its left child? The maximum element is 4, correct? And what is the minimum element from its, what is the minimum element from its right child? That is 7. So that means that 4 is lesser than 5 and 7 is greater than 5. That means it is a BST. It's satisfying the condition. So for that case, what will be the minimum? Minimum will be int max, the, maximum, integer value that we have in integer, and the max will be int mean. Okay, and the final answer will be again 0 because it is not a, I mean, it, although it is a BST, but it is, empty. So that is why. So we need to also take care of the, the leaf node as well. So basically, if uh, it is a leaf node, right? Then we also need to return something like this, but not the same. Let me tell you. Although this is, a leaf node, it is also a BST, and the size is 1. Okay, because there is only one element present right here. The size is 1. And what will be the left? For example, I am at 1. I'm right here at 1. So what is the minimum? Because this is the only one element. So the minimum is itself and the maximum is itself as well. Okay. So for that case, I'll be using the roots value for the minimum and maximum. Okay. And the final answer is 1. Now everything is done. Okay. As I have already told you initially that, let me remove this person. Yeah. I have already told you in the beginning twice that I'll be parsing the information of the children to its parent. Okay. So how will that be going to happen? So well, if I will find out the post data traversal, Post-order traversal means that means I will first go to the left subtree, then I'll go to the right subtree, then I will try to access whatever data I'm currently having. I mean, for I know whichever node I'm currently at. So I will access that particular thing, and I will try to move upward. That means it is a completely bottom up fashion traversal. Okay. Then we will access. Let's say. Okay. So isn't it the posterior traversal? Yeah, so this is it, and we will actually doing that. So as I have already taken care of the base conditions, now I will be moving to the left and right. Okay, let's say the left information is call it L and right is R. So get size will be like left. Okay, moving to the left, and the right thing will be the right information will be moving to the right separate. Okay, and collecting the information. Cool. So till now what I have done is I have just traversed both the left and right subtrees and collected the information. Now I have the information of its left and right child, correct? Likewise, I have already told you, for example, I'm right here in 5. I have the information of both 1 and 8, correct? So let's say that I have an answer, okay, which is basically this particular structure. I just need to return to my parent. Okay. So if I just found out the left and right information for any particular node, then can I say the size of whatever I'm going to return, the size will be, for example, I'm right here at 5, right? So what is its size? The size will be whatever its left side plus whatever its right size plus itself. Okay, itself means 1. That means 1 plus 1 plus 1 is the total size of this particular subtree. So for that I will be writing 1 plus L dot size plus R dot size. That means left plus right plus itself. Okay. So here I just have found out the size of the subtree, and now the work is done. Now I just need to take care of few things. For example, if the left subtree is a BST and the right subtree was a BST, if these two were the PhDs, and only then I will take care. I'll think that okay, my children's are PhD, then am I also satisfying the condition with them? For example, these two are PhD and 5 is also satisfying the condition for PhD. That means its left child is lesser than it, and the minimum element of its right child also greater than the root element as well. So for that, it is a BST. So we will need to take care of that particular thing. That means if the left is BST and the right is also a BST, and then I will see, okay, if these two are BST, then whether I am actually satisfying that particular condition. So I'm sorry. So roots value, let's say, is greater than whatever the maximum value from its left child. That means L dot max, and roots value should be lesser than whatever the minimum element in the right side. I mean, it's right children. Okay, then only I will say, okay, this is a PhD, isn't it? So that means I will say answer dot each PhD, because I am just returning this piece of information to my parent wherever I am currently at. So is this true? Is this a BST? Yeah, this is a BST. Okay. So yes, this is a BST. Then what is its minimum? So, well, its minimum I'll be returning is, if this is a BST, then the minimum will be the minimum of entire subtree, okay? And the maximum will be the entire subtree, correct? So for that, I need to find out minimum of, let's say, root value, right? And left's minimum, whatever the minimum from the left subtree I just have found out, and similar case for the right subtree, correct? And as I have just found out the minimum, similar case for the maximum, you know, value, correct or not? Yeah. So cool. I just have found out it, if it is a BST, and if it is a BST, then what is its minimum and what is its maximum? Now, one thing is left out is final answer, because I just have found out the size already. So, so the final answer is nothing but the size itself. Okay, answer dot size. So why answer dot size? Because see, every subtree may not be every subtree may not be a BST, but for every subtree I'm just finding out its size. Okay, size of the entire subtree. So whenever I'm just verifying that okay, this particular subtree is a BST, that means whatever size I just have found out, that will be the size of that particular BST, isn't it? So that is the case that I'm, that is the thing that I'm doing here. And as I have already found out things, then I will simply going to return my answer. Correct? Now, if this particular condition was not met somehow, that means what? That means wherever I am currently at, I mean, which particular tree I'm just currently looking at is not a BST. So if it is not a BST, do I need to take care of the minimum and maximum value? No, because this is not even a BST. It is not satisfying my condition. So for that case, I'm just required to return whatever the final answer is, from here. So what is the, let's say, this is not a BST, the subtree which is rooted at node 5 is not a BST, just think about it. So for that case, I'll be returning, whatever the final answer for its left child and whatever the final answer for its right child, their maximum. Correct or not? So for that case, I will be simply going to, uh, final answer will be nothing but maximum of its left's final answer. Ultimately, I am requiring my final answer. Okay, that is what I am concerning about. And R dot final answer. So I just have found out everything. Now, as I have reached right here, that means this particular condition was not met. That means it was not a BST. So I just need to tell that, okay, wherever I am currently at is not a BST. That is why I'm just, need to write that, okay, this is not a BST. Set the flag and just return the answer. Correct? So this is it. This is the entire solution. I hope you enjoyed it. Okay. So basically, I hope you got it. Let us try it. If there would be a syntactical error or something, let us try it. Otherwise, this is a perfect solution. Okay, this is correct. Submit it to see whether it is actually working or not. And it worked. So guys, this is the solution, and this is, pretty much clear. Okay, I mean, pretty much intuitive. So basically what we have done till now is we just have, done a, post order traversal, and for each node we are just returning this piece of information to its parent, correct? And the parent is basically holding the information, both its left and right child, based on the fact that whether, it is existing or not. That means, for example, 1 doesn't exist, so it is existing, so it basically holds the information of 8, that okay, is this a BST? And if it is so, then what is its size? What is its min and max value? Okay. At the same time, we are just uh, verifying, or we are just updating our final answer as well. Correct. So yeah, so this is it. And note that we are just moving from bottom of fashion. Okay, so wherever I am just finding out the subtree is a BST, that means I'm actually getting the maximum value, because for example, I'm right here at 1. Okay, I just have found out, okay, this is a BST. Now I'm right here at 5. I found that this is a BST. Let's say I'm right here in 10. I found out this is a BST. That means I I am continuously having even more higher size than before. Let's say I'm at right 1. The size of BST is 1. I'm right here in 5. The size is 3. That means it is bigger than the previous one. Similarly, let's say I'm right here in 10, and let's say this is a BST, this entire tree is a BST, let's suppose. So then I would have even larger value, even larger size than the size I got before. So that was I saying, that was the benefit of moving bottom of fashion to get the maximum result as possible. So for that, I am just returning this piece of information, 5 information, to its parent, wherever I am currently at, and based on that, I am just finding out the result. I hope you liked it. I hope you enjoyed the entire video. And if you did like it, then please hit the like button, and just share this such solutions to your friends, colleagues, so that it would be helpful for everybody. Okay, and please do not forget to subscribe the channel, and because if you subscribe, then you will get more such videos continuously, because I'm just posting such videos, such kind of videos, which is more important every week. Okay, twice or thrice in every week. So please subscribe to the channel, and hit the bell button as well. So thank you for watching, guys. Stay safe. Thanks.